Hi, and welcome to this section of the Physics 2 tutor. And in this section, we're going to conquer a core part of this course that you really have to understand before you can go on and do any of the remainder of the material. The good news is it's a pretty easy concept once we explain it through the example problems. And what you'll find out is it's really not that big of a deal. And you also have a lot of everyday experience with the general concepts of what we're going to talk about in this section. And that's going to be the concept of heat. I bet that everybody watching this video right now has an idea in their head what heat actually is to them. And you'll find that your common sense ideas of what heat is actually pretty much what we're going to define it mathematically to be here in this physics course. We're just going to put some rigor behind it so we can calculate and put numbers behind heat. Well, first of all, let me back up for a second from heat and let's review a little bit about temperature. We said that temperature in the previous couple sections ago was really a measure of the internal energy, so to speak, the vibrations going on inside of a substance. It's sort of the aggregate measure of sort of the average, energy state of what the material has inside of it, how much agitation, so to speak, the atoms have. The higher the temperature of a substance, the more the atoms or molecules are just jiggling around, and the stronger they're kind of bouncing around and vibrating in there. And the lower the temperature, of course, the motion is slower and so on and so forth. And if you go all the way down to absolute zero, there's no movement at all. The atoms are just completely motionless, okay? Now, the concept of heat is related to temperature, just like you might think of in your everyday life. Heat, what do you think heat actually means? Well, in physics, we are going to define heat to mean, okay, and I don't really necessarily want you to memorize this definition, just kind of listen to me and internalize it. Basically, in order to raise the temperature of something, you have to give it heat. You have to add heat to an object, okay? That's really is a definition of heat. Temperature is what we actually measure with a thermometer. In order to raise the temperature of something, you have to add heat to it. In order to decrease the temperature, you have to take heat away. Or another way of saying that is the object must deliver or lend its heat or give off heat to the environment for its temperature to go down. So you can think of temperature as sort of the measure of what the substance actually has going on inside of it energy-wise. In order to lower that temperature, this substance must deliver heat to the surroundings. In order to raise the temperature of this substance, we must deliver heat to the object. And that makes perfect sense. I mean, when you have a pot of water on the stove, room temperature water, it's at a certain temperature. We all know that we light a fire under that pot of water. What we're doing there is we're delivering heat to the pot, and that heat is going into the atomic motion or the molecular motion of the water, and it's agitating it more and more. Eventually it agitates it so much that the steam comes off the top, and we'll actually talk a little bit more about that in the next section. But here we're going to talk about heat, and we're going to put some math behind it. Now, the only thing you're going to have to get over when we talk about this is that if from here on out in the entire course, when we talk about heat, the actual equations that involve heat, the symbol for heat, you would think it would be an H, right, for heat. It's not. And there's a good reason for that. We're not going to talk about it now, but it's not called H. Anytime you're talking about heat in physics, you're talking about Q. You have to burn that in your head and just get over that. It looks a little bit weird in the equations. Every time you see Q, you've got to think of a fire under a stove delivering heat to your object, or some sort of blast chiller taking heat away from your object. Q is heat, and that's just sort of the way it is, okay? I think the way I want to proceed at this point is just to go ahead and write an equation on the board relating heat and temperature, because we said heat and temperature are interrelated because delivering heat raises the temperature. We're going to write that relation down, and everything else that follows is just going to fall out because of it. So basically what you need to know, and this is the only equation that you'll have to really even be exposed to in this section, and it's a very important one. The amount of heat, Q, okay, needed to raise the temperature, and I'm going to abbreviate that temp for temperature, of a material is, and the good news is it's an incredibly simple equation. What do you think this equation is going to be? Let's just write it down. It's very simple. The heat required to raise the temperature Q is going to be equal to the mass of the substance times a constant we're going to talk about in a minute called specific heat times the change in temperature that you're trying to pull off here, okay? So let's go ahead and label this stuff and make sure we're all on the same page. Q. We said Q is what we're calling heat. The unit of this this should not be a big surprise to you, is the joule. Okay, you'll find out that in physics, it's very convenient and very neat the way they have it set up. You know, back in Physics 1, you're talking about potential energy and kinetic energy. Anything to do with energy, even work, in fact, was a means of adding energy to a system, really. The units of that are joules. This, when you really think about it, when you light that flame and when you put energy, so to speak, into the material, or when you add that heat, it's just a synonym for energy. When I say I add heat to something, it's just a synonym. I'm really saying that I'm adding energy to the thing. And that makes sense because think about, you know, you have a gas coming out of your stove, you know, natural gas, and it's burning with the oxygen, and there's a chemical reaction there that liberates energy. That's why it's hot, and that energy goes straight into the pot. So it's really and truly energy that you're delivering to it. We just use and deal with heat so much in everyday life that we give it a new word. We call it heat because it's, I guess it's just in its own little category because we use it all the time. But it's no different than any of the other forms of energy that you have. It's just a sort of a different result that it pulls off, being able to raise the temperature of an object. So in this equation, Q is simply joules. It's the amount of joules you're adding or subtracting to a substance, okay? M shouldn't be a surprise. It's the mass of whatever object we're talking about. Let me ask you a question. If I have a slab of copper in my hand that I can hold in my hand, and I put a flame, you know, a Bunsen burner or just a stove flame underneath it, it's going to raise the temperature a pretty good amount. Now let me ask you something else. Let's say I had a slab of copper or some metal, and let's say that it was very big. Let's say this slab of copper was the size of my house, okay, horizontally like this. Or let's say it's the size of a city block. It just goes on and on and on. Let's say it's thousands of kilograms, you know, of material there, and I have the same little bitty burner underneath. Do you think the amount of heat that I'm adding to this slab is going to raise this gigantic slab the same amount of degrees Celsius, the same temperature? Of course not. If you have a small material and I add X number of joules to it, it's going to raise the temperature by a certain amount. If I have a gigantic material that spans a city block and I add the same number of joules of heat to it, energy, well, the temperature is not going to raise so much. When you look at the entire material, locally it'll increase a lot, but when you look at the aggregate of the whole material, it's not going to raise the temperature of that whole material as much because there's so much more of that material there absorbing that heat. So of course you're not going to raise the temperature as much. So of course the more mass you have here is going to play into this relation, and we'll talk more about that in just a second. But that's why it's in the equation. This guy is very important. It's called the specific heat. Let me back up. When we're talking about mass, we're going to be talking about kilograms like we always do. Okay? Specific heat is a constant in this equation because different materials absorb heat. The relation between absorption of heat and increasing the temperature is different from material to material. And let me give you an example. Copper, very, very good conductor of heat. Aluminum, very, very good conductor of heat. That means that I do not have to put a copper pot on the stove very long, and that burner is going to heat up that copper very, very quickly because the energy going into the copper, the molecular and atomic structure of that copper just absorbs that heat and goes straight into the molecular motion incredibly efficiently. So the temperature is going to increase very rapidly for copper. Now, if I take water, forget about using a pot to hold the water, just the water itself. Okay, water, it takes a whole bunch more heat for water to increase the same temperature. You have to suck in a whole bunch of additional heat for water to increase the same temperature that it does for copper. So basically, in a nutshell, water is a poor absorber of heat when compared to something like copper. And that's why this goes into this equation here, because it depends on the material. So this specific heat is going to be a different number for whatever material you're dealing with. The units of specific heat that we're going to deal with, we'll talk about it in a second. The units are going to be joules per kilogram degrees Celsius. I'm going to write that down here. I'm not going to talk about why the units are this way. I'm going to leave it like that for right now. I want to finish this guy out, and then we're going to talk a lot more about why this is defined the way it is, okay? Temperature, or I should say, notice this is not temperature. This is delta temperature. Delta, anytime you see a delta here, that is the change in the temperature, the final temperature minus the initial temperature. So this is going to be obviously in degrees Celsius in this equation. So you have degrees Celsius here. Your specific heat's almost always going to be given to you with a degree Celsius term, so we're using consistent temperature. So what does this equation mean? You have to ask yourself this question. What it means is, let's say I've got a slab of copper. Let's say we know that it has 2 kilograms mass. So I know it has 2 kilogram mass copper. I know the specific heat of copper because I look it up in a table. Let's say I want to raise the temperature of that copper by 10 degrees Celsius. So I know the mass, I know the specific heat, and I know I want to raise it by 10 degrees Celsius. All I do is take this, multiply by this, multiply by this, and what I get out at the end is a number in joules. That would be the amount of energy in joules that I have to add to this specific size copper block that I have in order to affect this temperature change that I'm trying to calculate. So you see, it's really a brilliant equation. Whatever you want on the right-hand side, you just dump the numbers in here. The mass of the specific size and shape of the material you have, the specific heat, which depends on the substance you have, and then how much I want to raise or decrease the temperature. And what you have there is you're calculating how much joules it takes to do that. And it works both ways. If I'm adding heat to the system, Q is going to be positive, and I'm going to raise the temperature. And if I'm trying to cool it off, I'm basically going to have a negative delta T there, because if I'm trying to cool it off, the final temperature will be less than the initial temperature, and what you'll get is a negative Q, and that means that energy is leaving the system, or energy is fleeing or going away from the material that you have. We'll talk about that a little more here in just a second as well. I want to spell that out for you right now. Basically, what I want to say is, and this is super important too, if Q is greater than 0, if I calculate a Q greater than 0, then what this means is, I'm going to put it like this, colon, what it means is heat flows in to material, okay? And what it also means is that the change in temperature increases. Delta T is greater than 0. When you see delta T greater than 0, what it means is the temperature has increased. The final temperature was greater than the initial temperature, so delta T is greater than 0. This is really important. When the Q is positive, by the convention that we're defining in our books, heat flows into the object. Now let's look at this. If you calculate a Q less than 0, meaning you get a negative number for Q, it doesn't mean it's some wacky amount of heat that's negative or anything. It just means that heat flows out of material. Okay, and because of that, what we're saying is the delta T is less than 0. So this is nothing magical here, people. It's just like way back in Physics 1 when you were talking about your equations of motion. You had to define positive x direction and the negative x direction. Negative x wasn't some mystical thing that was just a crazy thing, you know, in the 5th dimension or something. Negative x just meant it went that way instead of that way. We have to define negative and positive conventions in physics so that we can track exactly what the system is doing. This is exactly the same thing. If we calculate a Q, or if the problem tells you that Q is greater than 0, all it means is the system you're talking about, it means we're putting heat into the system. It means we have a burner underneath there and we're delivering Q into the system. This is very, very important for you to know. I don't want you to go to the next section until you burn this in your head, because it's going to screw you up if you don't keep it straight. So whenever you're looking at your problems, they're always going to define some system for you. It could be a piston moving. We'll talk about those later. It could be an ice cube. It could be a block of copper. It could be a pellet that you're dropping into a bucket of water. Whatever your system is, if Q is positive, you're putting heat into that system. Okay? If Q is negative, heat is leaving the system. So if you take like an ice cube, for instance, you put it, or let's say let me take a different example. Let's say we take this guy right here, this pen. If I put it in the oven, okay, if this is my system, the oven is delivering Q, is delivering energy to this pen, causing the temperature to increase, so heat flows in to this pen. Q is positive because Q is going into this pen. Heat is going into this pen. Now, scratch that for a second from your brain. If I take this pen and I put it in a freezer, which is a very cold environment, temperature is much less than this pen, what's going to happen immediately is heat is going to flow from this pen into the freezer. In other words, this pen is going to start liberating its heat to the air surrounding it in the freezer. The Q is going to go out from this pen, so Q will be negative. Q will be negative because heat is leaving the system, which I'm defining to be as my pen. Because Q is negative, heat is flowing out of my pen. Delta T is less than 0. And that just means that the pen's going to cool off. It's going to get colder. Delta T is going to be less than 0. That's crucial for you to know. You got to keep your sign conventions right in this stuff with heat, because if you don't, you're going to get the wrong answer almost all the time. In fact, you will get the answer all the time. Let's move on just a little bit. What I want to do is look at this equation right here. just follow me with this equation right over here. Let's rearrange this equation and solve for the specific heat. Because this is an equation. You can do anything to it. You could rearrange it just like you do in algebra. If you were to do that, you would find that the specific heat is equal to Q over M times delta T. All I did here is divide by M and divide by delta T. So the specific heat is Q over M delta T, which is right over here. Why am I doing this? Because I want to show you that when you look at it this way, think about it, the units, Q is going to be in joules, like you would think, because we're talking about that. Mass is going to be in kilograms, and delta T is going to be in degrees Celsius. So this is the units of specific heat that I gave you before. It looks like a crazy, crazy unit here. It doesn't make any sense, but I'm going to try to explain it to you why it's defined that way in a second. If you were to look at this and just look at the units of it, what does it say to you? You know, when you have in physics 1, meters per second, you read it as meters per second. You know what that means. Every second you go, you travel 1 more meter. In this case, the way you read this is, starting at the top, joules per kilogram degrees Celsius. Joules per kilogram degrees Celsius. So what this is saying, if you were going to write it out in words, is the specific heat is equal to the amount of energy needed to raise 1 kilogram of a material by 1 degrees Celsius. And you can see that from the units. When you think of it in terms of joules per kilogram degrees Celsius, what it means is if I have 1 kilogram of a material and I'm trying to raise it 1 degree Celsius, this is 1 and this is 1, so what I've got on top is joules. It's the amount of joules required to do that. So when you look in that table of specific heats in your book, they're going to be in joules per kilogram degree Celsius. When you look in your table of specific heats, what you're really reading is how much energy in joules does it take to raise that material, 1 kilogram of that material, by 1 degree Celsius. So let me give you an example, a specific example. The specific heat of water is given to be 4,186 kilograms per, joules per kilogram degrees Celsius. And for comparison, for copper, the specific heat of copper is 387 joules per kilogram degrees Celsius. Now, what does this tell you physically? What it's telling you is, for water, it takes 4,186 joules to raise 1 kilogram of water by 1 degree Celsius. Okay, 1 kilogram of water is not that much water. It probably could fit in your hand, okay? But it takes 4,000 joules, 4,186 joules to raise that much water by 1 degree Celsius. Now, it only takes 387 joules of heat energy to raise the same mass of copper by the same temperature, 1 degree Celsius. So you can see right away, by looking at the specific heats, that it takes much, much less energy to raise copper by the same temperature that it would to raise water. And that's what I was talking about earlier. Some things in nature have, an affinity for heat, and at the molecular or the atomic level, they take that energy in, they distribute it to all of the atoms very efficiently, and that heat transfer is really, really efficient. And so that's what copper is. It's an incredibly good conductor of heat. Water really isn't such a great conductor of heat. It takes a whole lot more than 10 times the amount of energy just to raise the temperature of water the same amount. And that's why when you put your pot of water on to boil, almost instantly your pot is scalding hot where you'll burn yourself if you touch the pot. But if you stick your finger in the water after 1 minute or something, the water is going to be warm, but it's not going to be boiling. It takes maybe 5 or 10 minutes to boil a pot of water. It's strictly because of the difference in specific heat, and that all boils down to what's happening at the quantum level, at the atomic level of the material you're talking about. So specific heat is different for every material because of that, because different materials absorb heat in different ways. So what we're going to do now is we're going to erase the board. We really have only presented one equation for you. This is it. Everything else here was just sign convention and just sort of trying to explain what specific heat really is practically. What we're going to do now is work a few problems after we erase the board, and I think you get a hang of how to use this. It's really not a difficult concept once we get some problems under our belt. Okay, now our first problem is going to go like this. You're driving a car down the road, and a driver slams his brakes in a car, so he's going a certain speed, and he slams on the brakes. The friction between the brake drums and the brake shoes, you know, the brake shoes go and they hit the drum there, and you're going to create some friction there in your brakes, and that is going to slow your car down. It converts the car's kinetic energy directly to heat, okay? If a 1,500 kilogram car traveling 30 meters per second comes to a complete halt, how much of does the temperature rise in each of the 4 brake drums if each brake drum is 8 kilograms? And I'm going to also give you the specific heat of iron for the brake drums is made of iron, 448 joules per kilogram degree Celsius. Now there's an incredible amount of information here, and it's really tempting just to throw your hands up and say, I have no idea. What you have to do in physics is write down what you think the problem's about. Number 1, always draw a picture. You've got to draw a picture. If you're not drawing pictures, you're just not going to solve it. You're not going to figure out what it's really asking you. So do that first. Write down your information and then write down what you know. You know it's talking about heat transfer. You know it's talking about specific heat. So write down the relation involving specific heat. We'll read it one more time just so it's clear. A driver brakes on an automobile and comes to a complete halt. The friction between the brake drums and the brake shoes converts the car's kinetic energy directly to heat. If a 1,500 kilogram car traveling 30 meters per second comes to a complete halt, how much does the temperature rise in each of the 8 kilogram brake shoes or brake assemblies? Okay, let's go ahead and draw a picture for that and figure it out. What we have, I'm not an artist, so bear with me. Here what we have is basically a car. We know there's 4 wheels to a car. And we know that this guy is traveling forward at 30 meters per second. We know this, okay? These drums in the brake system is 8 kilograms each, okay? And we know that the specific heat of the drums, because they're iron, is given to us at 448 joules per kilogram degrees Celsius. That's the standard units for specific heat. We know they're made of iron, so we know the specific heat of that guy. And last but not least, we know that the mass of this car is 1,500 kilograms. So I said there's a lot of stuff going on here. But fundamentally, you have to ask yourself, what is this problem doing? We know the car is going forward at 30 meters per second. So right away, you know the mass of the car, you know the velocity of the car. From Physics 1, you know how to calculate the kinetic energy of the car. It's 1/2 mv squared, and you should know that from Physics 1. You also know that the units of kinetic energy are joules, just like the unit of heat is in joules. So if the car is going 30 meters per second, and it has a certain amount of kinetic energy of motion because of that, and you slam on the brakes and the problem says that the kinetic energy is converted totally and completely to heat in the brake drums, then all of that kinetic energy you calculate has got to go into thermal energy, into heat, into going into those drums. So what we're going to end up doing is equating those two things together to calculate what we're trying to calculate, which is how much the temperature rises in these brake drums. So let's do one thing at a time though, because when you're starting out in this stuff, you're not going to be able to map all the way to the solution like that. What you're going to have to do is take it one step at a time. We know the kinetic energy of the car is 1/2 mv squared, which is 1/2 times 1,500 times 30 squared. And when you do that math, you will find that the kinetic energy is 6.75 times 10 to the 5 joules. The unit of energy is joules. And what we're saying in this problem is that when you slam on the brakes, all of the energy of motion goes into the energy into these brake drums. Okay, it's basically all of the energy goes into heat for those guys. And we know, basically from before, that all of this of the energy goes into heat of the brake drums. Basically, we're going to end up equating these things, okay? So the total Q going into all 4 of the brake drums is 6.75 times 10 to the 5 joules. This is the energy as it goes into all 4 of the brake drums because it takes four wheels to stop a car. But the energy of one drum is just going to simply be this number divided by 4 because there's 4 cars. So what you're trying to do is break it down to the drum level to calculate how much heat we're actually adding to each drum individually. And when you do that, you will find out that each drum receives 1.69 times 10 to the 5 joules. So I'm going to circle this kind of with a fuzzy line. It's not the answer, but it's an important intermediate step. What you've done at this point is you calculated the energy of motion, and you just divided that energy by 4 because we're saying that all of that energy goes into heat, into heating the brake drums from friction, right? That's what we're saying is going on here. Now is where you pull out what you know from what we learned today. We learned that the heat going into or out of a system is equal to the mass of the system times the specific heat times the delta T, right? So we know for one drum, because we're trying to calculate, the problem says how much does the temperature does the temperature increase in each of the drums? So we know each drum receives 1.69 times 10 to the 5 joules. We know that each drum from way back up here is 8 kilograms. We know this because that was given to the problem. We know that each drum is made of iron, and the specific heat of iron is 448. Now, all our units are consistent with joules and kilograms in degrees Celsius. So all we need to do now is calculate the change in temperature. So you take this number, divide by 8, divide by 448. The delta T is going to equal 47 degrees Celsius. And it's a delta. Delta T means the increase in the temperature. So whatever the temperature of those brake drums, whatever they were to begin with, they increased by 47 degrees Celsius. That's pretty hot. Now in real life, you know, they don't increase in temperature that much because this is a perfect system. We're saying all of the energy of motion goes into those 4 drums. Well, that's not really true. The rubber meeting the road takes a lot of the heat away. The transmission takes a lot of the heat away. There's lots of different ways. Heat into the wind resistance that's hitting the car, that's taking the energy away from the car. So this is a perfect example, but it's very illustrative to look at. By the way, you're going to deal with this a lot in physics. You're going to be dealing with these perfect systems where you're making these incredibly wacky assumptions, but it's meant to sort of make sure that you understand, you know, in general, what's going on. Real world's always more complicated. In this case, we're saying all of the energy goes into the heat of the drums. Well, that's not going to be the case, but it's a good way to exercise your muscles to make sure you understand what we're talking about here. Okay, drums increased by 47 degrees Celsius. The next problem is similar sort of slant to it, but well, we'll see the differences here. We're going to say for the next problem that water at the top of Niagara Falls has a temperature of 10 degrees Celsius. So you have a waterfall. The water is going over the top at 10 degrees Celsius, okay? It falls down to the bottom of the waterfall, which is a distance of 50 meters, and all of its potential energy goes into heating the water as it crashes into the bottom of the canyon or whatever at the bottom there. So all of that energy of potential energy that it had at the top, when it reaches the bottom, it all gets converted to heat, okay? So if it goes into heating the water there at the bottom, we're going to calculate the temperature of the water at the bottom of the falls. This is almost exactly the same setup as last time. You've got some energy sort of calculation. Instead of kinetic energy of motion, it's potential energy of this water. It's going off. We know how much potential energy it had. It's going to hit the bottom. We're going to assume magically that all of that energy goes into heat, and we're going to calculate the temperature rise, basically. What we're going to do first, I always recommend this, is to draw a picture. So I am not a very good artist, but this is my cliff. So you have water, you know, going off like this. Now, one thing we do know is this is 50 meters. Okay, the height is 50 meters. And we know that the water at the top here, right here, the temperature is 10 degrees Celsius. The initial temperature is 10 degrees Celsius. So what we're going to do is we're going to have a certain potential energy at the top. It's going to fall to the bottom, and when it gets to the bottom, it's going to crash into the rocks, and all of that potential energy it had at the top here is going to be totally and completely converted to heat, and it's going to heat that water up. That's what we're assuming here. Of course, real life's not going to do that, but that's what we're going to assume. First thing is, we're going to use our knowledge of Physics 1. The potential energy of anything above ground level is mass times gravity times the height above the ground. So in this case, we know there's sort of an impasse you're going to see right away, and you're going to scratch your head. We don't know the mass of the water here because, you know, in the previous example, we had a car. It had a certain mass. We could just plug that into the equation. I remember when I first started doing physics a long time ago, I would see problems like this, and I would throw my hands up almost right away because I don't know the mass of the water. The waterfall, it's just mass is flowing over it. I don't have any idea. It's not given to me in the problem. My best advice is when you're confronted with a situation like that, where it looks like one of the core variables in the problem you're solving isn't even given to you in the problem or even hinted at, 99.99% of the time, that variable is going to cancel out for the final solution. And that's just the way it's going to be. I mean, you're going to have to do that when you're dealing with Physics 1, Physics 2, electromagnetism, and Physics 3. When you're dealing with a problem that has a variable central to it that they didn't give you any information about, almost always that variable doesn't even matter. But the only way to see that is just to trust your instincts and push forward, and you'll see it. So what we're going to do is I'm going to tell you this mass is going to cancel, but I'm going to show you how. So what you're going to do is you're going to leave m in there because that's true. Whatever mass of it is going to matter, but we're going to leave it there because I don't know what it is. Gravity is 9.8 meters per second, and the height above the ground is 50. Okay, so what you're going to find out is this potential energy is going to equal, when you multiply these two things together, what you're going to get is 490 m, and that's in joules. Okay, 490, I left the m in there because I don't know what m is. All right, so let's go ahead and move forward. We're going to write that down. We know that this is true. Okay, now we're going to say that all of this energy that we have at the top here is going to be converted completely and totally to heat. And so the first thing we're going to write here is the heat is going to equal to mass times the specific heat times delta T. Okay, so what I'm going to do is I'm going to say, since this potential energy is converted totally to heat, I'm just going to plug it in here. 490 m is equal to m. Now the specific heat of water, you're just going to have to memorize after a while. I'm going to work so many problems with it. 4186 joules per kilogram degree Celsius. You're just going to have to, you're going to memorize that one because you're going to work so many problems involving water. That's the specific heat of water. Times delta T. Now this is interesting. Look what happens. The mass on the left cancels with the mass on the right. So the mass isn't relevant. What this means when you see a cancellation like this, it means that the mass of the water that you thought was so important to begin with doesn't even matter. The final answer isn't even related to the amount of mass to begin with because it cancels with something else that you're dealing with on the other side of the equation. But you'll only see that if you're brave enough to continue forward. I used to always get stuck on this step because I wouldn't know what to do. Just write it down and move on to the next thing. Almost always it's going to cancel. So all I'm going to do now to solve for delta T is I'm going to take 490 and divide by 4186. So delta T is going to equal 0.12 degrees Celsius. But don't forget, this is the change in the temperature, how much the temperature increased. It increased 0.12 degrees Celsius. But we noticed that we started with 10 degrees Celsius water. So the question clearly states, calculate the temperature of the water at the bottom of the falls. So temperature, the final temperature is going to equal the initial temperature plus the change in the temperature. How much did we start with temperature-wise? How much temperature did we increase? So it's going to be 10 plus 0.12. So the final temperature of the water is 10.12 degrees Celsius. So it increased just a smidgen. Temperature of the water increased just a little bit. So that's what you basically do. You're equating the energy of, in this case, potential energy, saying it goes into the heat, and we're calculating the temperature. Now, a lot of problems in this section, you know, when you're studying heat for the first time, are going to deal with that. So look for that in your problems. Look for something that you know how to calculate energy-wise and see if it makes sense to equate it to the heat energy going into or out of the system. That's generally what you're going to do. Let's go ahead and erase the board and work a few more problems to give you the hang of things. Okay, let's work our next problem. It says a 0.4 kilogram horseshoe, iron horseshoe, mind you, that is initially at 500 degrees Celsius is dropped into a bucket containing 20 kilograms of water at 22 degrees Celsius. What's the final equilibrium temperature of the system there? So what you have here is you have a bucket. This water is at, let's see, the water is at 22 degrees Celsius, so kind of like room temperature water. You have a very hot horseshoe that you have in a fire. It's an iron horseshoe. You heat it up to 500 degrees. You drop it in the water. Of course, that horseshoe is super hot. It's going to rapidly cool down. The water is going to rapidly heat up. And if you let it sit there long enough after all the steam goes away, basically they're going to both kind of approach the same final temperature. So the horseshoe temperature is going to go down. The water temperature is going to go up because it's going to get hotter. And eventually they're going to meet somewhere in the middle. Everything will settle down, and that's the final equilibrium temperature. That's what we really want to calculate. This is one of those problems where the first time you solve them, you're not going to be able to map out your path to the final solution in your head. You just need to start writing down what you know. And eventually you'll kind of take little incremental steps and get to the final answer. So as always, first thing we're going to do is draw a picture. And by the way, I practice what I preach. When I solve my own problems, I have to draw a picture all the time. if you're not drawing a picture, you're automatically violating the first piece of advice I'm giving you. We have a bucket of water, and we have a mass. We're going to say it's a horseshoe. I'm going to draw it like a square. The mass is equal to 0.4 kilograms, okay? And it's dropped into this bucket here, okay? This temperature here, the temperature is 500 degrees Celsius, and it falls into this water. The water, because it's water, it has a specific heat of 4186 joules per kilogram degrees Celsius. So that's something you're just going to have to memorize, the 4186. And a lot of times they're not even going to give you this in a problem. You're just going to have to know that, or you're going to have to look it up in your book. The mass of the water was given to us at 20 kilograms. And we're going to say that the initial temperature, T naught, let's call it, of the water, or you could label it TI, initial, whatever you want to call it, is 22 degrees Celsius. I believe those are all the numbers given to us in the problem. We have a bucket of water. Initially, it's 22 degrees Celsius, basically room temperature. It's 20 kilograms, has a certain specific heat. We have a horseshoe. The mass is 0.4 kilograms, 500 degrees. We drop it into the water. A bunch of steam happens and everything. Immediately, the water is going to go up in temperature. The iron horseshoe is going to go down in temperature, and basically everything's going to settle down and reach equilibrium, and we want to find out what that final temperature is. Okay, so the only way to proceed is to write down what you know. One more thing we know is the specific heat of iron, because you know you're going to need that since it's an iron horseshoe. Just look it up from your book. Is 448 joules per kilogram degrees Celsius. Okay? So what we need to do is we need to start using our knowledge and writing some equations down. The heat liberated by this horseshoe, because you're going to put it in the guy, and because heat is going to leave this horseshoe, we know heat is going to leave the horseshoe. Heat going away from the horseshoe is going to be mass times the specific heat times the change in temperature of the horseshoe, change in temperature of that horseshoe. Okay, so we know that the heat leaving the horseshoe is going to equal the mass of the horseshoe, 0.4, times the specific heat of the horseshoe, 448, times the delta T. Now for the delta T, the change in temperature of the horseshoe, we don't know what that is yet because we haven't calculated how the system behaves as it goes towards equilibrium. All you can write down is it's T final minus T initial. T initial is 500 degrees Celsius. This is important for you to make sure you really understand here. Everything we've written is exactly like the previous problems. The only thing that's different is that we don't know the final temperature of the horseshoe. We don't know it yet because it's going to go into this water and some magic's going to happen. Everything's going to reach equilibrium. That answer is going to be T final for that horseshoe, but we don't know what it's going to be yet. All we know is the mass, the specific heat, and its initial temperature. Okay? So when you crank through this and simplify it as much as you can, what you're going to have is 179.2 times TF minus 500. Okay? And if you just distribute this in, what you'll have is 179.2 times TF minus this number times the 500 is going to give you 89,600. The minus comes from here. So this is sort of the final relation that we have for the horseshoe. That's what the HS means. Now let me switch colors. Now that's what happens to the horseshoe. The horseshoe goes in and the temperature goes down, and we've written that relation. Okay? Now let's look at the water. The heat here in this system, if you look at the water, heat is going to be coming into the water because we're dropping a scalding hot horseshoe in there. So heat is going to go in. We're going to call that QH2O. And again, it's going to be the mass times the specific heat of the water times the change in temperature of the water. So Q for the water is going to equal the mass of the water, which is given at 20 kilograms, times the specific heat of water, which is 4186, times the change in temperature of the water, which again, I don't know what the final temperature of the water is, but I know the initial temperature is 22 degrees Celsius from here. So you can see where this problem is going. Here for the horseshoe, what you get is a relation in terms of the final temperature of the horseshoe. Here, for the water, once you dump the horseshoe in, I don't know the final temperature of the water either, but I know the initial temperature. So basically what you're going to have here is an equation for the final temperature of the water and an equation for the final temperature of the horseshoe. These two temperatures are going to be the same because after the horseshoe goes in the water, the bubbling and the boiling happens. Eventually everything reaches equilibrium temperature-wise. Those final temperatures of the horseshoe and the water are the same. So what we're going to end up doing is we're going to end up equating this heat here. I'm getting ahead of myself a little bit, but we're going to equate these two things and we're going to solve for the final temperature. That's where we're going. So Q of the water, if you do this math here, 20 times 4186 is going to give you 83,720 times TF minus 22. And just to continue banging it out, 83,720 times TF minus, and when you multiply this big number times 22, you're going to get 1.84 times 10 to the 6. Okay, so what I'm going to do is I'm going to put an asterisk by this equation. Go put an asterisk by this equation. We have an equation that talks about the heat that leaves this horseshoe because its heat is going to be leaving it going into the water here. And we have an equation for the heat coming into the water. When you think about it, every single joule of heat energy leaving that horseshoe has to go into the water. It has to because you're putting the horseshoe into the water. Every joule that leaves that horseshoe goes into the water. So we know that the heat leaving the horseshoe has got to be equal to the heat going into this water. We know that's the case. So what we need to do is equate these two things together. Once we equate them, we can solve for the final temperature. So let's do that right over here. There's one little gotcha that you've got to be conscious of. You've got to apply some knowledge of your physics and thinking about what the system actually is. You can't just equate them like this because you have to be very careful about your signs, okay? When you think about it, this Q for this horseshoe, this heat energy for this horseshoe, by definition is going to be negative. We always said negative heat means heat leaving the thing you're talking about. In this case, we're talking about the horseshoe. So we know that if once we know the final temperature and we do this, Q is going to be negative. So this will be negative. Q will be negative for the horseshoe. We know that Q will be positive for the water. We know this because Q is going into the water. So heat is going into the water. This is going to be positive. This is going to be negative. You simply can't just equate these things because if you have a positive quantity over here and a negative quantity over here, and one's negative, one's positive, you can't just equate them because you have a negative on one side and a positive on the other side. And they have to be equal. When you set an equation up, the left-hand side must really and truly be equal to the right-hand side, including the sign. So what you're going to have to do is you're going to have to put a negative on the front of this horseshoe stuff here, because what you're basically saying is all the heat energy leaving this horseshoe is going to be equal to all the heat energy going into here. So to make the left and the right-hand side both positive quantities, you're going to have to go ahead and stick a negative on the one side. There's lots and lots of ways you can wrap your brain around convincing yourself that this is what you need to do, but you got to think about that. When you're equating temperatures, my best advice is, when you're equating heat transfer, you got to make sure that the left and the right-hand side of the equation has the same sign. Because of our sign convention, we know this quantity is going to be negative. We know this quantity is going to be positive. So to make them truly equal, we're going to go ahead and stick a negative on one side so that the energy leaving that horseshoe is a positive quantity that we can then equate to the right-hand side. That's all we're doing. It's just a sign convention thing to make the equation work. So what we're going to do is we're going to take the negative of this side on the left, and it's going to be, let me switch colors here. All we're doing is sticking a negative 179.2 times TF plus, we're going to make this a plus because of the negative, 89,600. And on the right-hand side, that's going to equal 83,720 TF minus 1.84 times 10 to the 6th. Okay? And at this point, it just becomes algebra. What we're going to do on the left is I'm going to take this big number with TF and I'm going to subtract it from both sides. And on the left-hand side, I'm going to get negative 83,540 TF. I'm going to take this number and subtract it from both sides over here. On the right-hand side, I'm going to get negative 1.93 times 10 to the 6th. So I'm going to divide both sides by negative 83,540, and so the final temperature is going to be 23 degrees Celsius. Now, the other thing you got to do when you're solving these problems, you got to see if they make sense. Does 23 degrees Celsius make sense? Think about it. You've got a bucket of water at 22 degrees Celsius. You drop a 500 degrees Celsius slug of metal in there. It's a very small mass, but it's very hot into here. It would make sense that this water should increase in temperature. And it does increase in temperature. It increases by 1 degree. And so that makes sense. If you were to get, let's say, 20 degrees Celsius here, you would know that immediately your answer was wrong, because you know from experience the water should increase in temperature. And in fact, that's the kind of thing you can check yourself for when you're doing the sign convention stuff over here. If you get a nonsensical answer, you made an error here. And that's basically the long and short of it. So what we did is we wrote down the heat equation for one side. Okay, we wrote for the horseshoe, we wrote the heat equation for the water, and what we did is we equated the two to solve for the final temperature. It's not really a trick, but the only gotcha here is you got to think about the signs. You know this is going to be physically a negative quantity. You know this is going to be physically a positive quantity in the end, in real life. The heat going out is going to be out of the horseshoe is going to be negative because it's leaving the horseshoe. The heat going into the water is going to be positive. If you equate them, you're going to get totally wrong temperature. It's not going to make sense because you can't equate a negative quantity to a positive quantity. So what we're going to do is we're going to stick a negative sign on this to change that into a positive quantity, and we're going to say that we're going to deliver that much joules to the water. So once we do the equation there, we're going to calculate the final temperature and just do the algebra over here and solve for the final temperature. So let's do one more problem to give you practice with this, and then we'll be done with this topic. Okay, the final problem says lead pellets, each of mass 1 gram, are heated to 200 degrees Celsius. How many pellets must be added to 500 grams of water that's initially at 20 degrees Celsius in order to bring the water to 25 degrees Celsius equilibrium temperature? So what we have is a bucket of water, and in this case we're putting hot metal in it just like the last one, except instead of one big slug, we're throwing a bunch of pellets in there. And each pellet is 1 gram, and each pellet is 200 degrees Celsius. So what you're going to find when you do this is that each pellet is delivering a certain amount of heat energy to the water. And we're going to assume that we're going to throw these pellets in super quickly, one after another. Let's call it instantaneously. We're just going to throw them in one after another. And each pellet's going to deliver a certain amount of joules to that water. And what we want to do is calculate how many of those we have to add to raise the temperature of the water to 25 degrees Celsius. So, just like always, we're going to draw a picture. There you got your water. And this water, okay, the mass is 500 grams of water. The initial temperature of the water, T initial of the water, is 20 degrees Celsius. The final temperature of the water is 25 degrees Celsius. Final temperature of the water is 25 degrees Celsius. We know the specific heat of water is, again, 4186 joules per kilogram degrees Celsius, okay, just like we expected it to be. And what we're doing over here is we're adding these lead pellets into the water. So what we have, the mass of a pellet is 1 gram, just 1 gram. And the initial temperature of a pellet is 200 degrees, well, looks like I got too aggressive here, 200 degrees Celsius. So you just have to use your imagination. This little tank comes and does something like this, okay? 200 degrees Celsius. So what we're going to end up doing is the same thing before. We know that these pellets are going to deliver heat. We know the temperature of the water is going to increase. But in this case, we know what the final temperature of the water is. So the problem's a little bit different. So what we're going to do first is we're going to notice right away that we're dealing with 1 gram here, 500 grams here. We never want to deal with grams when we're talking about specific heat. This is kilograms here. We always want to be dealing with kilograms. So the mass of a pellet is 1 gram, and you all know that 1,000 grams is 1 kilogram. Okay, so when you're converting your units, you just write it like that. If this looks unfamiliar to you, go pick up the unit conversion tutor, and I'll teach you all about how to set your units up. But basically, we're converting units. So what you're going to get, the mass of one pellet is going to be 0.001 kilogram. Okay. And likewise, the mass of the water is 500 grams. And same sort of thing. 1 kilogram is equal to 1,000 grams. And you set it up that way to cancel your units. And so at the end of the day, it's going to be half kilogram. So that's the first thing you do. When you're working your problems, see if they give you any sort of units and in a weird temperature unit like Fahrenheit, or if they give you, like they did in this case, we'll give you units in grams and you're converting to kilograms, you got to convert. If you use the native units here in grams, you're going to get the wrong answer. It's just not going to work out. All right, so what we want to do next is we want to look at the water and we want to figure out how much heat is going into this water to increase the temperature like this. So for the water, we know that the Q going into the water, okay, is equal to mass times specific heat times the delta T. We know this, okay? And we know the mass is 500. I'm sorry, it's not 500. See, I almost fell for the oldest trick in the book. It's half a kilogram. You gotta work in terms of kilograms. Times the specific heat, 4186. Notice our units are consistent, kilograms with kilograms. Times the delta T. In this case, delta T is final temperature minus initial temperature. So it's 25 minus 20. Final temperature minus initial. This is the change in temperature of the water. So we have everything we need to actually calculate how much heat has to go into the water. Half a kilogram times the specific heat times delta T. When you do that math, you will get 10,465 joules. This is how much heat into water. This is how much heat has to go into the water. This has nothing to do with our final answer, but it's an intermediate step. So that's good. We made some progress. Now, in order to continue making progress, we know how much heat has to go into the water. We know we're adding this heat by delivering pellet after pellet after pellet. Each pellet delivers a little bit of heat because each pellet is at 200 degrees Celsius. Okay? So the way you do this is you say each pellet delivers. You have to look at it in terms of pellets. Each pellet delivers. QP, I'm going to call it for pellet. I'm going to call it the specific heat of the pellet times the mass of the pellet times the change in temperature of the pellet. Okay? In this case, we know that these pellets are made of lead. So we go to our chart in our book and we look up the specific heat for lead, and what it's going to be is 128 joules per kilogram degree Celsius. So it's 128 times the mass of each pellet we calculated to be 0.001 kilograms, okay, times the change in the temperature, okay? Now, the final temperature of these pellets, once they go into the water, the final temperature of the pellet is going to equal the final temperature of the water because they're going to reach equilibrium. So the final temperature is 25, and the initial temperature is the 200 degrees Celsius that we had to begin with. So we have everything we need to calculate how much heat energy is delivered over here. So QP is going to equal to 128 times 0.001 times that difference there. And when you do that math, you'll get negative 22.4 joules. Okay? And this is what each pellet delivers. And notice it's not a mystical, energy in another universe or anything because it's negative. Negative just means that these pellets deliver heat. What we're saying here with the negative sign for the heat delivered by the pellet is that when we put the pellet in the water, the pellet delivers energy to the water. So it's a negative quantity, just as we said in the beginning of this section. For the water itself, the water is accepting energy from the pellet, so it is accepting heat into the water, so the sign convention is positive. So the sign is really just keeping track of who's losing heat and who's gaining heat, and that negative sign came from the fact that the pellets actually decreased in temperature, and that's why the heat delivered there is negative. So what you can say by looking at it in total is that the water must accept 10,465 joules of heat, but each pellet delivers 22.4. So when you divide those two, 10,465 divided by 22.4, okay, that's the amount of heat per pellet, you'll get 467 pellets. So it's going to take 467 pellets to actually do this, and we're assuming that we're throwing these pellets in almost instantaneously. So you see, this is another example where the Q was negative in one side and the Q was positive, but we had to use our knowledge of the physics of what was going on to know what to do with that material. We didn't really need to carry the sign down here because we knew we're not going to get negative pellets for our answer. We know that the negative just means we're delivering heat from the pellets to the water. We know this positive means we're accepting heat from the pellets, so we can dispense with the negative. The negative is just there for our convenience to show us where the heat transfer is going. We don't have to carry it through to this step because we know what it's doing. It just means it's delivering the heat. So we take the heat accepted by the water divided by the amount of joules delivered per pellet. It's going to give us the total number of pellets there. So we've covered quite a bit of material in this section, and I hope it was clear for you. We've talked about the concept of heat. There's one little old equation that you really have to know, and it's this one. Mass times the specific heat times the change in temperature. That's going to give you the amount of heat needed to pull off that change in temperature. So we talked about that. We talked about what the concept of heat was. We talked about the fact that it just means you're adding energy to a system. Q is positive. If you're taking energy out of a system, Q is negative. You need to remember that because every section from here on out is going to really assume that you know that. And you know, you're really going to have to keep your signs straight, just like you might expect. So go ahead and try to commit that to memory. The specific heat is unique to the material. It just means that different materials absorb energy more efficiently, and they can affect the temperature change differently, you know, for the same amount of heat going into the system. And the mass is here just because, of course, it totally matters how big your object is, how much temperature change you're going to get after putting a certain amount of heat into the system. So go work some problems, keep your signs straight, do some thinking, and always draw a picture. And I think that you'll get the hang of working these heat problems.